Hello everyone, I'm Mohammed. I'm working as a data scientist in healthcare team at Johnson Labs. Today I will cover Johnson Labs native integrations with LangChain and HayStack. Here's the agenda. We will go over generative AI shortly and its challenges actually, and then the RAG architecture. After that, I will explain how you can implement document splitting and meta augmentation with Spark NLP, and then Spark NLP integration with LangChain and HayStack. Most of generative AI actually is the most popular topic in the AI world in these days. Most of the executives plan to build their own AI models and implement their production. And 75% of the CEOs say the companies have a significant advantage of generative AI if they implement this into their production and according to the competitive advantages. And they also say that there's an increase in the performance of the employees who use generative AI. But this is not easy, actually, because there's no control over the data and nor the models. So there are some solutions, of course, for this. I will try to explain that in this presentation. And the other one is bringing generative AI to production is also difficult, but you can handle this by built-in monitoring because it's really hard to monitoring that. And it's also too expensive at scale. Although the most popular model, GPT-4, is still having medical challenge problems because when you ask a question according to the clinical domain and it tries to answer or has some hallucination problem, it tries to answer with its own knowledge base, and again we have faced some hallucination problem over there. So we still cannot completely integrate the GPT-4 to our healthcare clinical productions. This is one of the most popular published, by the way. So here is the RAG architecture comes into play. Healthcare institutions and all the other domains already gathered their data internally in the case, right? So the thing that we want to do is asking the questions to the LLM, and we want it to answer our questions according to our data instead of using the LLM itself, right? This is the RAG architecture, what it does. So RAG architecture helps us to communicate with our data sets using the LLM models. In this way, we can use the LLM model role is minimized, and we use the LLM model as an orchestration here. Okay. Here is the summary of the RAG architecture. So we have a created data, right? We gathered some data internally, and then we need to split them into smaller parts. We name them as split, each of them. After splitting them into the smaller parts, then we need to vectorize them, right? After the vectorization stage, we need to save them in a vector database. On the other hand, we have some questions, right? We have some queries. So for answering the queries, we need to vectorize the question again with the same embeddings models. After the vectorization of the query, the retrieval part checks the similarity between the embeddings of the query and also the embeddings of the splits that we saved into the vector database. And it retrieves the top k most similar splits as a result. Okay, and we can do some pre-stage manipulations here, pre-stage processings here, and then we combine the query and the splits that we have and use a custom prompt, then send it to the LLM model, and the LLM model returns the answers according to only using our data, our splits actually. Okay, this is how the RAG architecture works. So there are just 5 stages in this architecture. It sounds like an easy process, but like source documents and document splitting. After that, we need to get the embeddings of those splits and save them into the vector database, and use an LLM model as an orchestration here for getting the results, getting the answers from according to our data sets. Okay, it sounds like an easy process, but it is not actually. You can do it with a 10 line of code. This is doable, but choosing the algorithms, choosing the strategies or the models at the behind is does really directly affect on the result at the end. So these are the stages that the developers can manipulate or can modify actually for their use cases. And the first stage is gathering the data. You can gather data from different resources, like if you have PDF files or you need to do some pre-processing over there, right? If you have PDF files or images, you need to convert them as a plain text or do some basic cleaning stays over there. And then if you if you are working on a medical data, for example, you need to do some metadata extraction over there, like entity linking or entity extraction or keyword extractions, etc. After getting data, then you need to split it into smaller parts. But splitting strategy is one of the most crucial one here, because it should be it is bounded to the domain actually, because if you are working on a granular token based task like a keyword extraction, you need to choose the chunk sizes here. You need to choose chunk sizes with a smaller number. But if you are working on a holistic tasks like summarization or Q&A, you can choose the chunk size with a larger number. But if you choose the chunk size with a too large number, okay, you can use some context over the over the data actually. Because why? Here is this choosing the embedding stage is important, because is a third stage. We need to choose the embeddings model. While choosing the embeddings model, we should consider the chunk size because it should be compatible with it. Like, for example, if you split the data with 1,000 tokens, okay, then if the embeddings model is not capable of getting the embeddings of 1,000 tokens, but just for 300 tokens, this means you will lose most of the context of your data, right? So this is why choosing the embeddings model is another crucial stage here. Like we need to consider the model size and its speed, of course, and also the scalability and the resources that we have. And the fourth stage is vector database stage. So we need to choose a retrieval strategy here, which we will use according to our use case actually, and also the resources like recursive, KNN, or BM25. Which one fits to your fits according to your needs, and you can choose that strategy, right? After getting the data, getting the splits from the vector database, you can still do some post-processing over there, like diversity or filtering or re-ranking the outputs, the splits actually, and then send it to the LLM model. The LLM model, again, we need to consider some other parameters here, like if it is an enterprise solution or not, or open source or not, I mean, or the model performance, or like the chunk sizes, context sizes, also the prompt templates we need to consider. Spark NLP replaces these just the two stages, like document splitting and also the split embedding stages. So we have some solutions for these two stages. Okay, so you can just integrate the Spark NLP into your LangChain and HayStack, LangChain and HayStack solutions actually. For the document split and the chunk augmentation in RAG, the splits should be document specific. We should choose the strategy according to the domain that we are working on actually, because the domains like medical, finance, legal, or the other domains have their own data structure, right? I mean the document structure. So we need to consider those structures while splitting the documents. Okay, it should be also context aware. Like if you have a table heavy content, you need to convert those tables to plain text using table to text, or if you have a charts, you need to convert them again. Like for the medical data sets, you can split your data using section headers in the clinical node, which I will show you. Also, you need to choose this ideal chunk and split size, also the overlap parameters over there. The metadata augmentation helps us to get the most relevant results from the vector database, and of course also the LLM model itself. Okay, so let's assume that we splitted the data in smaller parts, and the last paragraph, for example, doesn't aware of what's happening before then it, right? So we need to inject some information each splits and help vector database retrieval part for gathering the related splits from the vector database, right? Here is an illustration of the metadata augmentation in RAG architecture. As you can see, there's a query at the upper side of the left side, upper left side of the screen. Query is overdose complications of diclofenac. This is our query. Here is the similarity score. You can see that 0.78. This is the similarity score of the first text and the between the first text and the query that we have. But as you can see, there's no metadata information over there. But if we inject some metadata to our split, like the highlighted stuff at the below, in like patient ID or some other name of the document, or the published name of the articles, right? So you can add those kind of metadata information to your splits, and then here is the score 0.8 is the similarity score when we add after adding the metadata information. Okay, this is how it's important. This is why it is important actually, because we can eliminate the retrieval part will eliminate the irrelevant splits according to this metadata information. Also, it will help us to filter some of them after getting the splits from the vector database. On the left side, you can see a medical document. Like as you can see, there are some section headers over there, right? At the right side, you can see a default split, like default split from LangChain default split, like chart splitter using chart splitter, for example. As you can see, it doesn't consider the section headers here, but this is very crucial information. The section headers may be very crucial for metadata for clinical data sets, actually, clinical RAG architectures. Or because why? As you can see, there's a family history section here, right? And there are some diseases or the drugs. There may be some drugs over there that belongs to the family members of the patient. Okay, but when you split the data, like without considering the section headers, all these diseases of the family members may return from the RAG architecture according to our query, right? But if we split it with the section headers, like family history will be another split, and the principal diagnosis will be another split. So when we ask a query when we send a query to the vector database, it will return the diseases related to the patient himself or herself, right? Instead of the family members. Or if we ask a question related to the family members, it will return the splits that are that these diseases existing in the family history sections, Okay, but how you can extract how you can know the section headers in the clinical data sets. So you need to do some NLP stuff here, right? This is where Spark NLP helps you to do that in the metadata augmentation. The embedding stage is the most expensive stage of these 5 RAG architecture stages. Okay, as you can see in the left side, there are some embeddings models that you can use in your RAG architecture. Like, but since Spark NLP sits on the shoulders of the Apache Spark itself, so you can run your datasets on distributed systems using Spark NLP instead of running on a single node. For example, on the table at the right side, as you can see, for 1 million nodes, 1 million nodes on a single node, when we want to get the embeddings of the 1 million node on the single node, it takes 43 minutes. Okay, but if we use it 16 workers and distribute the jobs into all these workers with Spark NLP, so we can get the solution in just 3 minutes. Okay, this is how you can use Spark NLP for using your resources while using your resources effectively, actually. Johnson Labs has 8 different libraries NLP for solving the problems in the NLP domain, actually. So we have some of them are open source and some of them are licensed, like Spark NLP, Healthcare NLP, Finance, Legal, and Visual NLP. And we collected all these libraries in a single library, Johnson Labs. So when you just pip install Johnson Labs, when you do that, you will be able to use all the capabilities of these libraries, except the NLP Lab library. Okay. Also, we support the LangChain and HayStack RAG frameworks. Llama index we don't support yet, but it's on the way. Actually, we will do it very soon. So you can use the same notebook or same environment instead of jumping between the environments. You can use the same environment that you are using the Spark NLP libraries with LangChain and HayStack. When you just install the Johnson Labs library, you will be able to use all the capabilities of LangChain and also the HayStack libraries. For the metadata augmentation, Spark NLP for healthcare helps you to augment your splits with the metadata, augment your metadata of your splits in the healthcare domain with more than 2,000 pre-trained models and pipelines, actually. You can do some entity recognition or relation extraction between the entities, or assertion status, negation status, or do some mid-stage processing with Q&As or summarization models, and augment your data accordingly. Let's go over the notebooks and show you how you can implement the Spark NLP library on your use cases. Like, we have Spark NLP workshop repo here. As you can see, you can find any resources in this repo. So you will be able to use when you will be able to use Spark NLP libraries when you check these notebooks. Okay, so in this repo, we have Generative AI folder. When you click on this, you will see 3 different notebooks here. Like, the first one will show you, I will cover all of them in the session, by the way. The first one will show you how you can use Spark NLP for healthcare library in the metadata augmentation. Okay, and the other ones explains how you can use Johnson Labs library with the LangChain and HayStack integrations. Okay, let's start with the first one, augmenting document splits using this Spark NLP library. We install some libraries that are necessary for our session, and you need to upload your license here because Spark NLP for Healthcare is a licensed library. So you need to have a license, and then just import the libraries that you need to work on it. Okay. After installing those libraries, then you start the session using the NLP.start function. And now we have a Spark session, right? While splitting the medical documents, we have a document splitter annotator that helps you to split your documents in a flexible way. Actually, it's too flexible. We have several parameters inside, like the chunk size, chunk overlaps, split patterns, and patterns are regex or not. Or you can explode the splits as a new rows, for example, like split modes we have, like char mode, token wise or sentence wise, like recursive or regex. And all these options are available when you want to use Johnson Labs library, okay, for document splitting. We have 50 empty samples clinical notes here in our repo. We just download it. And then here is how a clinical note looks like. Like there are some section headers here, as you can see, like principal diagnosis or secondary diagnosis, like some medications, as you can see. So we will try to split the document using the section headers here and get their embeddings and then save them to the vector database. Okay, how we can save them to the vector database. Also, you may have some additional informations, not only the section headers or the entities inside the clinical notes, right? You may have some document IDs or the patient IDs, for example. If you want to ask a specific question if you want to ask a question with a specific patient, right? You need to have a patient ID or something special for this patient, right? And if you inject this information to your metadata, you will get a relevant results with that patient, right? So we added here a synthetic patient ID and document ID, and we convert our data set to a Spark data as a Spark data frame. Okay. So for the LangChain, and we load our data frame with a PySpark data frame loader, since we have a PySpark data frame right now. And when we use recursive char text splitter from the LangChain library, here is the splits look like. As I explained before, it doesn't consider the section headers, and it just splits the documents just using the chunk size and the chunk overlap information inside, right? And these are the metadata that as a metadata. Okay, how we can augment this, how we can split the data using the section headers or add some additional information to our metadata, right? So the first problem is that the entity recognition. Entity recognition, I mean, we need to extract the section headers first, right? What kind of section headers do we have in this clinical data set? So we create a basic pipeline, an NER pipeline actually, and we use the NER GSL Slim model here, and we write this only because this model has several entities inside, but we are interested in on the section headers, right? So when we run this on the sample clinical node that we defined, that I showed above, these are the section headers in this clinical node that we have. But what if we have some other section headers in our data set, right? So we run the pipeline, our NER pipeline, entity recognition pipeline, on the Spark data frame, whole data frame. And this is the list of the section headers that we have, unique section headers that we have in the data frame data set, empty samples data set. Okay, so just using the document assembler and document splitter from the medical, this is the last version, I mean, we can split the data set according to the section headers here. Like we set the set split mode as regex and set split patterns, just a list of the section headers. Okay, so when we run this, as you can see here, all the sections has been splitted correctly, as you can see, like social history, family history, past medical history, medications. Okay. You can also do that with token wise. I mean, you can set a token threshold, like maximum length of tokens for the splits. Then each split will have just 50 tokens at most. Okay. This is the example of that. Assign section header for each split. We can do that. How we can do that? We need, for example, you may also have some documents that is clinical documents that you don't know the section headers inside, right? Because and for assigning the section headers to your splits, you can use our clinical section classification model. Okay. Then when you run your splits on this classification model, it can assign the section headers directly. But here, we will assign for each split, for showing this, we will assign the section headers for each split that we have. Yeah. As you can see, each rows represents the sections, represents the splits that we have, and these are the section headers of those splits. Okay, you can also do that. So when we export the results here, like family history is history, represented as history. Like operation performed is procedure. These are the section headers, right? So then, if you have a large amount of data, large amount of corpus, for example, that you need to process or interrogate RAG architecture on it, but it is too large, and when it is too large, it's too expensive, right? So if you can do that, if the summarized version of those documents works for you again, you can use the clinical summarization model in Spark NLP and summarize this clinical note, like this one, for example, and then split it into smaller parts. Okay, like this is the summary of this clinical note. You can split it into smaller parts, or just use this part as a split. Okay, as another split. Yeah. So here here is the data frame that we assigned to section headers, as you can see. And now you can, if this is not enough, you can add some more additional information also. Like, for example, using the clinical entity recognition models in Spark NLP, you can, if you are interested in some of the labels, like some oncological data, if you are working on, and you need some oncological labels over there, and want to query, want to have some splits according to your query related to those kind of specific entities or the labels. Okay, so you can just create a pipeline like this, and we just showed here NERGSL enriched model here, and then it has several labels inside. Or if this is not enough, again, if you want to have the splits from the retrieval part, according to the ICD-10 codes of the clinical conditions, you can just use NER models in Spark NLP and like whitelist according to your needs, according to the clinical domain. Or you can detect the drug and drug NER models for detection of the drug entities, and some mapper models for checking their actions and treatments, right? Because some questions may contain some specific formats, like what kind of drugs can be used for anticoagulant action, right? So for asking this kind of queries, you need to have some disinformation in your metadata, right? So you can use drug action mapper, action treatment mapper in your pipeline. Also, RSNOM codes of your drug entities, you can ask a question according to the Aristotle codes when you have the Aristotle codes of the drug entities, right? You merge them and check their assertion status and just filter the present entities using a whitelist, right? And in this way, you will drop all the rest of the entities that has some other negation status like past or family member or something else, right? And then we get the embeddings and route the problem entities, clinical conditions, to the ICD-10-CM generalized model, and route the drug entities to the Aristotle model, okay? And when we do this, here are the drug entities in our sample clinical nodes, okay? And these are the clinical conditions detected in the clinical node we have. And here is the NERGSL model output. Yeah, this is a prettified version of it actually, like admission discharge, oncological, section header, or heart disease, right? Like disease syndrome disorder or cardiovascular disease, etc. You may have all these entities, all these informations in your splits, right? As a metadata. So here is a sample split. So when we run this sample on the pipeline we have, on the model we have, so these are the entities detected in this section, and these are the other ones. Okay, like here, for example, as you can see, the drug action, like we have a split like this. Let's assume that we have a split like this. When you run this split on the pipeline we have, so we can check the drug actions and the treatment specifics. Okay, we can add them as a metadata. Let's jump into the other notebook that we have, medical chatbot drug integration, Johnson Labs and LangChain. So we import some libraries here and then start a Spark session using the CPU machine here. And then Johnson Labs LangChain integrations, it's too easy, actually. You can use just, when you import the LangChain document loaders, you can format your documents when you use the text loader, or and also for using the LangChain specifics in the for document splitting and also the embedding stage, you can use the LangChain and HayStack capabilities under the Johnson Labs library. How you can do that? Just you need to import the LLM and you need to import the embedding retrieval from the Johnson Labs.LLM, and then Johnson Labs LangChain chart splitter. This is the LangChain chart splitter actually. You don't have to go out of the Johnson Labs library, and then the output will be the same with the LangChain. Okay. For the custom document splitter that I explained in the previous notebook, you can use this one, for example, like Johnson Labs LangChain custom document splitter. In this way, what happened? You are now able to use all the capabilities of the Spark NLP and the LangChain libraries together under for the embeddings and the document splitter parts. Okay, under the same roof actually. So like LangChain custom document splitter, when you set this, like set split mode as regex and set split pattern is section headers we have. Okay. And for the embeddings stage, these are the embeddings model that you can use. This is the NLU representation actually. So from Johnson Labs LLM, embeddings retrieval again. So we define embedding stage here, like embedding retrieval, Johnson Labs LangChain embedder, and we can use this embeddings model or all the other ones. Okay. Yeah, these are the vector databases, and you can use the LangChain itself for the vector database in the LLM model. For the LLM stage, you can again use the LangChain and also the HayStack, right? We have some sample data set here, PubMed diabetes, 1000 rows here with the metadata. As you can see, PubMed ID, abstract, and published date, title, and also the full journal name here, which we can use them as a metadata inside, right? We load our data set, load our data frame using the PySpark data frame loader, and we can check the metadata like this. So we have 1,000 documents right now. And when we want to split them using the chunk size as 500 and chunk overlap as 50, using the Johnson Labs library, LangChain chart splitter, now this text contains all the splits according to these parameters, okay? So we just defined the GSL splitter here and split the documents accordingly, okay? For the embeddings part, we can define the embeddings model here, and we use the instructor-based embeddings model here, and you can check the embedding size using this, like this is a test, and this is the embedding size. Also, after splitting the documents into smaller splits, now we have nearly 4,500 rows, right? At the beginning, we have just 1,000 rows, okay? And this is the first, these are the first 3 splits that we have, like document here, and other one here, and the other one here, okay? As you can see, this is the splits, okay? And this is the metadata, as you can see, this, okay? For the vector database, we used files here from the LangChain library, and we define the database here. And from the documents, as you can see, we feed our splits, also the embeddings model inside. Then it writes to the vector database. And when we run the files retriever, okay, when we run the retrieval part, we can set the top K here. So according to this, when we set it as 3, it will return just 3 splits, okay? And as you can see, it takes too much time. Why? Because the embeddings part is the most expensive one. So you can use this on a distributed system and get the embeddings on using Spark NLP, for example, or on a distributed machine, like Databricks or something else, okay? We already uploaded the vector database on our repo, so you can just download this and use it by loading from local. And when you run a query over there on this vector database, cause of diabetes, these are since we set the K as 10 here, okay, you can modify it. We have now 10 different splits, okay? Like these are the metadata of those splits. But if you want to have some diversity over there, because if you don't want to have the same splits from the same documents, right? We can use the diversity parameters here, like lambda mode. If it is closer to 0, it will be more maximum diversity, okay? So you can set these kind of parameters and get the diversity solutions. Like this is the previous one, and this is the other one. As you can see, some rows has been changed. The order has been changed, right? There's an issue named lost in the middle in the LLM world. What happens if you have 10 rows, 10 splits? The LLM model remembers the first rows and also the last ones more than the middle ones. Okay, because it's working like a human behavior, right? Because when someone tells us a story, we especially remember the first of it and the last of it. We are tend to forget the middle stage of the story, right? The LLM is the same, so we need to reorder it. We need to reorder the splits that we have. Why? Because they are sorted according to the similarity scores here. So instead of sorting it to 1, 2, 3, 4, 5, 6, we can sort it as 1, 2, 3, 4, 5, 6, right? In this way, we will collect the most relevant ones in the at the each sides, right? At the two sides. So instead of doing this manually, you can use the long context reorder module in the LangChain library. So it will reorder it accordingly. Then you can use it. Like you can use the BM25, which extracts keywords and do some statistics over the data and over the splits and return accordingly. So there's no embeddings here. It's cheaper, but the accuracy. So we can discuss on the accuracy actually. So you can use the retrieval BM25 as a retrieval part. You can also ensemble both of them, FICE retriever and also the BM25 using the ensemble retrieval, like by setting some weights here and set the top K here. Okay, you can do that. For the LLM part, we'll show you. I'll show you how you can use OpenAI. You need to enter your OpenAI key here and define the LLM variable here. Like we imported the retrieval Q&A and also the chat OpenAI model from here. We used the GPT 3.5 Turbo in this demo, and we create a Q&A chain here, like retrieval Q&A from chain type. We defined the LLM first, and as a retriever, we use the FICE retriever here, and return source document true. This means the metadata. Okay. So when we run this query on this chain, as defining the query here, like the question, so this is the result. What happened here? The LLM model answered this question using just only the splits we provided. Okay, by using its default template. So we can update the template here. With a custom one, you can use the custom one. Like you can restrict the behaviors of the LLM model, like saying, do not use your knowledge base, or just use the information I provided. If you don't know, just do not try to make up an answer. Or like here, if you have an answer, just say, it's my pleasure at the end of the sentence. So you can just chain type keywords as a Q&A chain prompt that we defined here, as you can see. So at the end of the sentence of the LLM model, it's my pleasure to help. So it's using the prompt that we provided, right? Yeah, you can also find some examples of the Llama 2, also the Zephyr in this notebook. Okay, I will jump into the HayStack. So this is very similar actually. Like we import some libraries here, and for using the GPU, you need to install this one, farm HayStack all, and we start a Spark session using the GPU hardware. After that, Johnson Labs HayStack integrations, like for using the HayStack processors, you can use Johnson Labs HayStack processor. Again, this is the similar logic with the LangChain actually. As you can see, for the embedder, this is the same, like Johnson Labs HayStack embedder, and you define the embeddings model here and document storage that you want to use. These are the embeddings model that you can use. We have a sample data here, and from the embedding retrieval from the Johnson Labs.LLM, we defined the Johnson Labs HayStack processor, which will split the documents into smaller parts. Okay, this is a stage. Okay, and then we have the process docs, and this is document number, a split number that we have at the end. After that, we will use in-memory document store here. As a document store, we defined this. Then for FICE document store, you can use this one. For the embedding stage, like embedding retrieval, document Johnson Labs HayStack embedder. This is the embedding retrieval, and the embedding model will be the embedding model name that we want to use here. And the document storage, we already defined here, like the in-memory document store, and we will use the GPU. This is another stage, right? And now we will create a pipeline, like HayStack pipeline. Okay, we define a pipeline and then add node by node. This is too modular, right? This is very modular. So pipe.add node, we add the component, the processor. So it will split the documents first and as a preprocessor, right? After that, we will add another node as a retriever. It will embed and retrieve the results, retrieve the splits, okay? So when we run a query on this pipeline with this, so these are the most top K relevant splits that we have, okay? Yeah. You can also create dogs, and you can define some functions like this for making much more flexible in your workflow. And you can use the for the LLM part. You need to define the LLM processor, right? After setting the HayStack process, splitting the documents, we set the embeddings model, and then set a custom prompt here, as you can see. And this is the custom prompt node. And then here, we created a pipeline. We imported some libraries like diversity ranker and lost in the middle ranker. So we created the pipeline. And now we added, as you can see, we import some libraries like diversity ranker and lost in the middle ranker is a pipeline. We defined the pipeline and add node by node to your pipeline, like diversity ranker, lost in the middle, and prompt nodes. And when we run the query, we have the split that are related, right? After that, you can use the LLM models like Google Fluent 5 Large or Mistral AI or Zephyr here. Now, I have covered all the steps that we have right now, so we can go over the Q&A stage. Thank you.